Okay, thank you very much. So let me start by saying thanks to all the organizers for putting up this conference. It's my first time in Prague. I'm loving it. I really like the city, and the building, everything has been super good so far. So thanks a lot. And thanks for giving me the opportunity to talk. I will talk about time-like Liouville gravity, which is a 2D theory of quantum gravity, and the computation of its sphere partition function. And from the start, I want to say that I'm an ignorant in string field theory, complete ignorant. So I will tell you what I've done and try to make a few connections here and there, but please feel very free, well, more than free, feel very encouraged to ask questions and to make comments, not just ask questions, but maybe you can fill in the gaps or make observations or comments where you feel it can be of interest to the rest of you. Then also before I start, I wanted to flash a group of my collaborators, some of whom don't need any presentation here. But the first part of the work I'll present, I did with Atish Tabulkar, who was my PhD advisor, and Harold and Mate, who, as I said, don't need any introduction. And I think Harold is online, I saw just before, and it's 3 AM for him, so good for him. He also, I should say thank you to him, but he was trying to tell me a little bit what more the connections with string field theory were, what the motivations you might have for this, so thanks. And then the second part of the talk is work that I did with Dionysios Aninos at King's and Beatrix Moolman at McGill. And right now I'm working on time-like Liouville with boundaries, and this work that I'm doing with Aditya Bawane. And hopefully I'll have some time to talk about it at the end of the talk, but let's see how it goes. All right, so let me start, and I'll start with a very brief introduction. So we'll start by considering the Euclidean path integral for gravity. And one thing we can do is that we can go to the conformal gauge for the metric. So this means that we use diffeomorphisms to, from the physical metric G, we single out omega, which is the conformal factor, and H is some fictitious metric. And then the path integral for gravity, of course, integrates the metric, and in particular, in this gauge, integrates the conformal factor omega. And then the Einstein-Hilbert action, so the action for gravity, in this gauge has this kinetic term for the conformal factor. And famously, or infamously, this kinetic term exhibits this minus sign here. So it has a wrong sign kinetic term. So this is a well-known problem. It's known for, well, here is the dimensions. This is just a problem that shows up in any dimensions. Actually, here I have D, you see. Well, yeah. So here I'm still in the dimensions, and then now we'll go to 2. But this problem of this minus sign, it's in any dimensions. And as you probably all know, it's a problem because it means that this Gaussian action is unbounded from below, and therefore we don't know how to perform this integral. One of the subtleties of the path integral of gravity in this gauge. So indeed, as it was said, now I cannot, perfect. If we go to 2 dimensions, then the metric is reduced to the conformal factor, because basically we can use the 2 diffeomorphisms in 2 dimensions to fix the fiducial metric H completely. And therefore the gravity, if you want, is just, given by the conformal factor. And therefore here the path integral of gravity will only have this integral, and it's a way of simplifying the problem or singling out a problem. So it's a good way to study this problem. We go to 2 dimensions. And then on top of that, in 2 dimensions, if you couple gravity to conformal matter, the effective action that you obtain from integrating the matter is the Liouville action, or the Liouville theory. This is also known for a long time, since Polyakov in the early 80s, and the Liouville theory is a theory that is also well known, been studied a lot, has been solved almost completely. So this is good. And in particular, to be a bit more concrete, the way it shows up is that this is now in 2 dimensions. The coefficient that's sitting here in front of the kinetic term is roughly given by the matter central charge. So then if we want to reproduce this minus sign of the path integral of gravity, basically we need the central charge of the matter to be positive. Okay. In particular, positive and large, if you want a good semi-classical limit, and I will explain this in more detail. I will go over all this. Then the regime of the theory, then becomes the Liouville theory. And the regime of the theory where this kinetic term again is negative, just like here, is called the Timelike Liouville regime. It's the Timelike regime of the Liouville theory. It reproduces this minus sign, and therefore this is the regime that I'm interested in studying, precisely because it reproduces this problem. Now, Timelike Liouville, in this Timelike regime, because of this minus sign, the theory is non-unitary. And the quantization of this theory took a bit longer to understand, but it is now known that it is a conformal field theory. So a few years ago, there was some work on this from the bootstrap, and it was understood that it's a well-defined conformal field theory. So this is good because then we can use the machinery of the bootstrap for gravity. And the final comment that I wanted to make is that, as I was saying, we couple it to matter with a large and positive central charge. So this means that this is a model of gravity with unitary matter, so coupled to unitary matter. So yeah, philosophical. Well, because there we know how to solve the path integral. You know, things are better well defined. And then
usually, but not here. In this case, you have a lot of problems because of unboundedness. So
yeah, it's true. I mean, actually, once you solve this problem, you could say, okay, then you might as well start with just the Lorentzian path integral and find out how you should do the contour of integration. And it's definitely the next question to explore.
And the second question is, people have been trying to do with complex metric. Why not?
Well, I mean, yeah, I think in general, the approach is that you take omega to be real to start with because you want a real saddle. For instance, one of the motivations why we studied the path integral on the sphere was because the sphere is a Euclidean de Sitter, and that path integral reproduces the entropy of the de Sitter horizon. And in that case, you want a real saddle. But it's your question is very relevant because, as I will show you, actually this path integral seems to require a complex saddle also, in which case you would have a complex sphere. So let's see. I mean, yeah, you can consider everything. Eventually, you can put constraints depending on the physics that you want. But it's true that as a path integral, if you put this in complex place, and actually we will be complexifying things. Yeah, it's a valid question. But in principle, I assume that here the contour of integration is real to start with. Okay, so this is the model that we want to study, and we want to ideally make a model of quantum gravity from this. And so the questions that we wanted to address were, first of all, can this Timelike Liouville theory be a consistent theory of Euclidean 2D gravity with a cosmological constant? And so the step that we took in this direction was to study the spectrum of this theory. So we did the BRST quantization, the BRST associated to diffeomorphism, so really the gravitational spectrum. And then we studied what happens with the finites, with the correlators in this theory, and we checked whether they were staying finite and crossing symmetric, because this is a CFT. So this was a consistency check, if you want. So this is what I'll show in the first part of the talk. And then here I just wanted to make a comment, which is maybe connected to what might be a motivation for you for this, which is that Timelike Liouville is a good example of a theory with a string theory with a time-dependent background. So I will show you in a second that Timelike Liouville has a time-like linear dilaton, and it also has a tachyon, which is an exponential that is time-dependent. So it's a good model to study time-dependent backgrounds. And I'm sure this is a field on its own, and I can do no justice to it. I just wanted to mention this paper by Strominger, the work by Strominger and Takayanagi, which was actually, as far as I know, one of the first papers, if not the first paper, where Timelike Liouville was mentioned, or the word was coined. And there was, well, they saw that that was a solution to closed string theory, that it had this exponential tachyon that was time dependent, that was growing in time, and they studied the closed string pair protection, for instance. So actually the first paper in Timelike Liouville was in this context. Okay. In which yeah, so if you have, so the question was, what is the interpretation of the exponential Liouville wall? So indeed, if you want to do quantum mechanics, you plot this potential. It's an exponential potential, as I will show. And in space like Liouville, it's just like a normal exponential. So you have this wall. In time like Liouville, that interpretation is a bit more weird, if you want, because if you have a positive cosmological constant, the potential would go down, actually. If you have a negative cosmological constant, the potential goes up just the same. So for instance, if you put Timelike Liouville on the disk and you want to study ADS solutions, it would be the same potential wall, and then you can study, for instance, branes or things like this that are on that barrier. At the level of the CFT, even if you have a positive cosmological constant and the potential is going down, you nevertheless see the same type of reaction that you see when the potential goes up. So maybe the quantum mechanical or the mini superspace interpretation is not so clear, but at least at the level of what happens in the CFT in terms of reflection of the potential wall, this goes through the same. So I don't think there is a very good mini superspace interpretation of the potential wall going down, as far as I know. But at least at the level of quantization, the reflection property goes through. It's probably not a very satisfactory answer, but the mini superspace analysis of Timelike Liouville has not been done properly. Yeah. I know Harold like studied it and worked on it for a while, and I think at some point he got frustrated and stopped it. But yeah. What is it? Yeah. Yeah, all sorts of problems you encounter there because of hermeticity, and yeah. Okay, then the second question was, okay, say that we can make a consistent model of 2D gravity with this theory. Can we compute something? And in particular, can we compute something with the path integral that we know it's not well defined to start with? And for this, an interesting observation is that Timelike Liouville with a positive cosmological constant has a solution, which is the sphere. This is nice because for those who know, space like Liouville does not have such a solution. Because it has a sphere, basically we can do Excel point approximation around the sphere, and this is what we did. We computed this path integral perturbatively. So this was about figuring out how to deal with the contour and how to deal with the volume of the diffeomorphisms in the path integral, which I imagine is something that you're also interested in. And here I wanted to make contact with something that I guess is also your interest on this, which is that this path integral partition function on the sphere is supposed to be reproduce this finite on-shell action of the string theory background. Here I wanted to mention this work of Raghu Stanford Yan, who also computed this sphere partition function, as far as I understand that case, for a phase-like Liouville coupled to minimal models. And of course, in string theory, this is a very fundamental quantity. And I think for a long time, it was supposed to be zero because you divide by infinity, which is the volume of the residual diffeomorphisms. So the question was whether it's zero or not, but it seems that there is an infinity also in the numerator, so one can get something finite. So this is the results that I will present that we did. Okay, so that was the introduction. Yeah, please.
It's just a small comment regarding the space like Liouville. There is actually a saddle you can find, but it's like a weird saddle with a minus signature. which
okay.
appeared in our paper. So if you take space like Liouville, but you consider minus d theta square minus sine square theta d phi square, that is a solution. Basically,
Oh, I see.
you turn the contour of the mini superspace mode vertical, and
I see.
that's basically what went into the analysis in our paper. So we're also doing semi-classics around that family.
Okay, I see. So it's a real cell, but with this
Well, you can think of the omega as having some I pi, you know, so it pulls out a minus sign overall in front of the metric.
Okay, I see. Yeah, there are also cells if you fix the area. In fact, that's how it's normally studied. But okay, okay, yeah. Thank you. Thanks. Okay. So this is the outline, and I will first. So I'm sure some of you know Timelike Liouville very well, but I'm sure also there are some people who don't. So it's always good to start from the beginning, and I'll just start by reviewing how Timelike Liouville gravity appears. So again, we start with the path integral into dimensions. I will only look at spherical topologies, so that's why I put this 0 here, but I'll drop it afterwards. This is the same as this. So we have the integral over the metric and the volume of diffeomorphisms. These xi's represent the matter. And as I said, this is a conformal field theory matter. This is our assumption. We also have the cosmological constant. It's a key ingredient. And then we're in 2 dimensions. Therefore, we can go to the conformal gauge where now this fiducial metric h mu is completely fixed. So then the path integral for gravity turns into a path integral for omega, where now it's a scalar field. So this becomes scalar field theory in a fixed curved background. So this is one of the beauties of 2 dimensions. It's just scalar field theory. So then we do this gauge fixing, and the measure over the metric becomes a measure over the conformal factor. And then we have the BC ghosts of the gauge fixing, and we obtain their corresponding action. So in the path integral, we get these 2 measures and the measure of the matter. Okay, now the point is that because the matter is a conformal field theory, and so are the ghosts, their actions do not depend on the conformal factor. And therefore, we can just integrate them out, and they go out of the omega integral. But they have the conformal anomaly, the trace anomaly. This means that actually their measures do depend on omega, and therefore when we integrate them, they leave behind an effective action for omega, which is this one here. So this factor here is just this one here, where square root of g becomes square root of h e to the 2 omega. Now I've rescaled this mu naught is just mu because I've rescaled some free factor here. It's just that rescaling. And so this is the action, this Gaussian piece with the linear term and this cosmological constant, which now becomes a vertex operator in this theory. And then the trace or the footprint of the matter theory appears now in this coefficient. Is only in the coefficient of the kinetic term if you want. And this q squared, if you do the derivation properly, is given by this. So I've just called it q squared, but this is what comes out of the derivation if you want. So this coefficient depends on the trace or the conformal anomaly of the matter sector of the ghosts, which is the famous minus 26. And then there is this +1 also. And this +1 actually is coming from the fact that the measure of omega itself also has a conformal anomaly. So all this coefficient is accounting for the anomaly of the matter sector, of the ghost sector, and of the conformal factor. So this is the matter minus 25. So because of this, then the semi-classical limits that I will be considering will be implemented by q squared going to infinity. Yeah. Okay, so now we have this action here, and we want to normalize it canonically. So we're gonna put this q squared inside, and I'm gonna rename this omega. With q omega, I'm gonna call it a new field, and that is the Liouville field. That's the last step that we need to take. We just reabsorb q in omega, we call it chi. And then the action that we're left with in the path integral for the conformal factor is this Timelike Liouville action, which is this thing here. So notice now there is no Q squared here anymore, and this is what we get. So again, this is a scalar action. So this is the gravitational action, and it's just a scalar in a fixed curved background if you want H. So H, we can fix it. So in general, it's fixed to the flat space or the sphere, but otherwise it's just curved background. Again, it has the Gaussian term. It has this linear term where now Q is sitting here. Q in the Liouville literature is called the background charge. And then again, we have the cosmological constant p, which now has become this vertex operator. And I've introduced a new parameter beta here that I'll come to in a second. Beta is called the coupling, the Liouville coupling constant. Now, why is it called Timelike? Well, for you, it's very obvious, which is because if chi is a coordinate of the target space, this is the Timelike coordinate. Okay. Then this action of this theory has a very important property, which is that even after we have fixed diffeomorphisms to the conformal gauge, there is a residual gauge invariance, which is given by this transformation here. So if we have, this was our conformal gauge, where now omega is this chi over q. So clearly, if we do a Weyl transformation of the fiducial like this, but we shift chi accordingly, the original physical metric is left untouched, it's left invariant. So clearly, this is a gauge invariance of the theory. And in particular, when H is fixed to the flat space, this is the conformal symmetry. So this is the origin of the conformal symmetry of the theory. And because it is gauge, in this case, the anomaly has to vanish. All the anomalies, all the conformal anomalies have to vanish. So now I can go back to this beta parameter that we introduced here. Why did we introduce it? Well, because the path integral has to be gauge invariant, has to be conformal. Classically, this term with this would be to the 2 chi over q, and classically this would be invariant. Yeah? Or I can repeat the question. Well, depends on the question.
Well, right now to start. Conformal flat space, okay. But a question I was asking myself for, when you consider Riemann surfaces, you have three classes of Riemann surfaces: the sphere, the torus, and the higher dimensional. So, if you fix the flat metric, you are actually on the torus, because you cannot fix globally the flat metric, the flat metric on the sphere. No, but she was saying that it was doing the thing for the sphere.
Yeah, I'm considering spherical topologies in general. Can I not fix? Yeah, maybe. Yeah. Yeah, so I think typically, so the way it's considered is that you trade it indeed with a follow-up of the Liouville field. You assume that the Liouville field folds off, I think, like a logarithm with a Q indeed. The fact that the Q is called the background charge is precisely because you can see it as a charge at infinity. So I'm not sure I fully understood your question, no, but. Okay, maybe we can talk. Up to this follow-up, then we can put it on flat space or on the sphere, and then we have conformal symmetry, conformal invariance. Okay. So now just the last comment about beta. As I was saying, this term has to be conformal invariant, or in other words, this vertex operator has to be marginal. So it has to have conformal dimension 1. Classically, it does, because this would be chi over q, as we renamed it. But this operator has an anomalous dimension, just like any vertex operator. And therefore, for this term to be invariant also at the quantum level, we need to add this parameter to allow for the classical plus the anomalous dimension to be equal to 1. And if we impose that, then we obtain a relation between Q and beta, which is this one here. And it's a well-known relation of Liouville theory. If you've seen Liouville theory, you know this for sure. So this is, if you want, the classical relation, and this is the quantum relation. And remarkably, this is actually an exact relation. So it's an all-loop relation. So this is one of the beauties of Liouville theory, that with simple calculations, you actually compute a lot of the quantum effects. In fact, if you invert beta in terms of q, you see that beta is 1 over q minus 1 over q cubed, and it has all the infinite corrections. So then the semi-classical limit was either q going to infinity or beta squared going to 0. Okay, so this is going to be a parameter of our perturbation theory. Okay, and just a few more comments. Now, the central charge of this theory is given by 1 minus 6q squared. The 1 is just because it's a scalar, and this 6q squared is actually the classical piece. So this is the trace of the stress tensor already classically, and it's again due to the presence of this background charge at infinity. But then if you recall how we defined q here, this is how we had defined q. If 1 minus 6q squared is the central charge of Liouville, then it means that the sum of all the central charges is 0, so there is anomaly cancellation as it's required by the theory. Then one thing that we can do is map the complex plane of the central charge of Liouville. And so here, then you can see the different regimes of the theory in full glory. So the regime where the central charge is smaller than 1, so when q squared is positive or q is real, this is the Timelike regime. It's the regime where, again, so this is smaller than 1, therefore C matter in general is bigger than 25. So it's we have a central charge for matter that is large and positive. In particular, in the semi-classical limit, q goes to infinity, so the central charge for Liouville is very, very negative, and the central charge for matter is very, very large and positive. That's a semi-classical limit we're interested in. But one could consider the other region where now q squared is actually negative. So the central charge for Liouville is bigger or equal than 25. And equally then, the central charge for matter is negative. So there is the matter that becomes non-unitary, if you want, in general. And this is the space-like regime. It's called space-like because there is an analytic continuation that you can perform, which is the following. So the analytic continuation of Q is because we have to make this negative to go to Liouville central charge very positive. So we analytically continue this, but then to have a real action, we also analytically continue the field and the coupling constant, B or beta. And then we land on this action, which now has a kinetic term that is positive defined because of this I here. And this is why this is called space-like Liouville. And in fact, this is the standard Liouville theory that people studied for many years. And it is the well-known Liouville theory where Liouville is unitary in this regime. And it was what was understood as Liouville gravity for many, many years. So both regimes are related by this analytic continuation. But one of the difficulties for Timelike Liouville for a long time was that this analytic continuation does not work at the quantum level. So not all correlators analytically continue well under this continuation. But now this has been solved and there is a good solution for Timelike CFT also. Okay, I think I've said everything I wanted to say. So are there any questions before I move on? Yeah.
I just wanted to ask, which set of works are you referring to when you say the bootstrap, they solve the Timelike Liouville using the bootstrap?
So the first solution was for the 3-point function, so the structure constant for the 3-point function. This was what was well known to not analytically continue well from the space-like 3-point function, which was the famous DOCZ formula, for those of you who know, otherwise don't worry. But basically, what was found was a new solution to the bootstrap equations, and that was done by Samologikov, Kostov and Petkova, 2005 or so. So this was an independent solution for the 3-point structure constant. But then it was the question whether this 3-point function solved all of the bootstrap equations, because it's found from a subset initially of some recursion relations, which are a subset. So then what remains to be done is to check whether the solution that was found for the 3-point function solved all the bootstrap equations. And this was shown numerically by Liouville and Santachiara in 2015. And they showed that it is finite and crossing symmetric. In fact, I'm going to talk.
Which were the last two authors you mentioned?
Liouville and Santachiara. In fact, I'm going to show them here. This Liouville and Santachiara.
Okay,
I'm going to talk about this just in a second. Yeah. Yeah, this is actually important because it's going to become relevant in just a minute. Okay, so now let's see what is the spectrum of this theory and whether we can make sense of this theory at the quantum level. And so the first thing we wanted to compute is the spectrum of this theory. So the primaries of this theory are given by vertex operators, because in this case, chi transforms linearly under this conformal transformation. So exponentials are the natural primaries. And they are labeled by this alpha, which is called the Liouville charge. And the conformal dimensions are given by this. Again, this alpha squared is like the anomalous dimension of the vertex operator. And this is due to the presence of the background charge. So the question for the spectrum is, what is the range of alphas in the spectrum of the theory? It's convenient to parameterize this Liouville charge like this, where E now can really be understood, or is the energy in field space. So it's the charge associated to time translation, to chi translations. And then if you plug this here, you get, these are the conformal dimensions. And again, the question of the spectrum is, what is the range of energies? In general, one can think that we want real dimensions. So energies can either be real or imaginary. So the question is, what is the range? Now, the conformal gave an answer to this question, precisely related to the question of Raghu, which comes from, again, the bootstrap equations. So the bootstrap is we impose the crossing symmetry of the 4-point function decomposed in this way, the product of two 3-point functions and the conformal blocks. And the point is that if you know the 3-point functions, then by demanding that this is finite and crossing symmetric, you can figure out what is the range of integration, so the spectrum of the theory. I've written here this 3-point function, that this was precisely this 3-point function that was found. It's not the same as in space-like Liouville. It's not important, the formula, I just put it here because it's really not trivial. It's an algebraic expression analytic that's impressive, and it is known exactly. But basically, if we want this to be finite, we have to check for the poles of this 3-point function and, of course, of the conformal blocks. So basically, we look at the poles of this expression here. These are upsilon functions. They're just some products of double gamma functions. It's not important, but basically, this guy only has zeros. This upsilon function only has zeros in the alphas. And therefore, we just look for the zeros of this denominator. So we check this, and we check the integrand, and we by inspecting this equation and the conformal blocks, it turns out that the integrand has poles on the imaginary axis of the energies. So if the S here, I mean the S channel. So these are the internal energies. Okay, so I say, okay, then good, maybe then we integrate over real energies, yeah.
Can you recall, please, how this result differs from the usual space-like result? What are the differences?
Yeah, so I think this part is more or less the analytic continuation of the DOZZ formula in space-like, but this part is not, and effectively is like the inverse. So the DOZZ and this Timelike 3-point function are related to each other by elliptic functions. So one is equal to the other times some products of elliptic functions, which actually diverge precisely when you go to central charge, real and smaller than 1. And effectively what these elliptic functions do is that they invert, basically. So the DOZZ looks a bit more like this is in the numerator and this is in the denominator. And then the big difference also is that here, this is a product of these 3 epsilon functions. And so there is a product for each one of the charges, alpha 1, alpha 2, alpha s in this case. So here you have these zeros determined by each of these, while in the DOZZ, here you have epsilons that have sums of these charges. Each epsilon has sums of these charges. So the poles depend on relations between the momenta. While in the Timelike case, it's not like that. The poles are just particular values for each alpha, independent of the other. Yeah, this is going to become important also. Yeah, I put alpha S because here is the S channel. So here we would have 1, 2, S, S3, 4. Sorry, yeah, the alpha S is the analytic behavior we are looking for because we want to figure out what is this control of integration. Yeah, so also I talk about alpha S or ES independently simply because, I mean, they are 1 to 1 here. So either say Liouville charge or energy. Okay, so this has poles in the imaginary energy axis. Therefore, okay, let's integrate over real energies, which on the other hand is nice because one expects real energies. But then one finds that actually this integrand diverges for energies large, positive or negative. Therefore, we cannot integrate over the real axis. And what Ribot and Santa Chiara realizes that actually a good prescription is to nevertheless integrate over the imaginary axis. And then you just give it an I epsilon away from the imaginary axis to avoid the poles. So it's kind of an I epsilon prescription. And they showed that with this prescription, you get a crossing symmetric and finite 4-point function. So this was established as the spectrum from the bootstrap, so imaginary energy. But of course, then the question, can you pass me? Thank you. No, I think now we both did it at the same time. Now it has overshooted. I need to go back one slide. Sorry. Okay, the question is that this is what the bootstrap tells you, but is this really the spectrum of the theory of gravity? So this is what we wanted to answer, and then we said, okay, then let's study the BRST cohomology of this theory. So the BRST cohomology associated to diffeomorphisms. Okay, this is the question. Is this a spectrum of 2D Timelike Liouville gravity? Okay. No. And now it overshoots. Now we go back one slide, 2 slides actually. Yeah, this one. Okay, this is the slide. So indeed, we compute this BRST cohomology for Timelike, and this had been done for space like Liouville, so we did just generalize it. These are the authors here. And the main idea is that just like in critical string theory, the states in the BRST cohomology are in one-to-one with states in the light cone gauge, which is manifestly free of negative norm states. This is the main idea of the result. So I'm not going to go into the details because it's anyway not so very enlightening, but just let's see the result. So this would be a general state of the theory. We have, these are the gravitational excitation modes. B and C are the ghosts. They are acting on some vacuum. This is the vacuum for the ghosts. E is the vacuum of the Liouville field. We have to borrow one scalar from the matter sector to create light cone coordinates in target space, and this is these are its oscillators. P is the momentum of these modes in the momentum in target space. So this energy and this is momentum. And from all the states, the physical states are the one in the cohomology associated to the 2D homomorphism, so to conformal symmetry in this case. And then if you compute that, you find that the states in the cohomology satisfy that this has to be equal to 0, where n are the number operators as usual. And since they are all positive, they all have to be 0. And so therefore, you don't have any ghost excitations or excitations of the time-like field. So there are no negative norm states. And then the interesting thing is what is the spectrum that this leads to. And for this, one imposes the on-shell condition, which is del not equal to 0. And roughly, this is what you get. So, okay, forget about this piece, but this is the L naught of the matter sector, if you want. The perpendicular is because it's everything else. This E squared and this piece is what's coming from the time-like Liouville. So the conformal factor sector. And this is what's coming from this X field that we have. This is the light, the other momentum in the light cone, if you want. And so the point is that if you have, for instance, free scalars, so this is critical strings, this would be the excitations of the other modes, and this would be in general positive and large. So therefore, you would be able to get real energies. And in general, the real energies are also in the spectrum. But because now you also have this minus q squared here, that's coming from the time-like Liouville sector, you are also allowed to have some imaginary energies. So eventually, the spectrum that's determined is real energies and a bounded part of imaginary energies. So both real and imaginary. So this is also work that we did with Mate, by the way. There is also just one caveat that I can comment, that's why I have this star here, is that, of course, not all the states in the cohomology satisfy this. There are some discrete states, and one has to treat those properly. Those allow for excitations of the ghosts. But here. So there are some discrete states that would have ghost excitations, but actually those are removed once you impose that your matter sector is unitary and Hermitian. So in the end, you get a spectrum that's free of negative norm states and ghosts. And then the observation is that the bootstrap determines imaginary energies for to have a consistent crossing symmetric 4-point function. And the BRST associated to gravity allows for real energies also. So there is a mismatch. And the question is, can we have correlators that are well-defined also on real energies? Or in other words, what is the prescription to analytically continue the 4-point function to real energies? So it's well-defined on imaginary energies that we know, but can we define it also on the part of the spectrum that has real energies? Yeah. If it's short, I can repeat it.
Okay. Yeah, so in normal Liouville theory, there's a distinction between the operators that can be on the outside, whose correlators you're computing, and the operators that run in the intermediate channel. Here, the e's on the vertical axis, are you also going to run them in the intermediate channel or only put them on the outside?
Yeah, that's a good question. That's the crux of the matter. Indeed, no. So real energies are not gonna run in the internal states. One has to make that distinction.
Oh.
We cannot, because otherwise the 4-point function would diverge.
So the result by Ribault and Santa Chiara only applies to external energies that are also imaginary, not to every other energy. Okay.
Well, I mean, they would say, in fact, the conclusion of their paper is that Timelike Liouville does not exist. That's what's written in the abstract. But simply because they understand Timelike Liouville with, they thought it was real energies and they vetoed that. They said there are no real energies in the spectrum. But in fact, you can be more flexible in the sense that you can define what's the internal spectrum, which is determined by the bootstrap by consistency of having crossing symmetry and finiteness of correlators. But that doesn't force external states to be also in that limited spectrum. You can actually analytically continue, and as long as you're careful, that is fine. And there is no inconsistency with crossing symmetry. Or in other words, you don't need to define your spectrum by the like identify your spectrum with the internal states in the OP or in the.
Okay, so the question you're asking is whether, just to summarize, the question you're asking whether the 4-point function for the external parameters can be continued to these real energies.
Correct, exactly. That's exactly. It's good to you anticipate all the slides. Perfect. Yeah.
Just a point. The BRST, about the BRST analysis. Okay, when you do the usual Liouville, you have not you can think about many ways, but one way is that you have fewer space dimensions or space-time dimension. Okay, you are subcritical. Okay, but you have unitary meta. As far as I have understood from what you wrote before, if you want to do Liouville theory, you should have not unitary meta, because you need, so you should have in some sense not the usual space-time bosons, because you should have some X with a negative central charge. So you should continue the X to imagine to be imaginary, or what else? What I didn't get.
No, wait. Maybe I'm not sure I understand the question, but I think it's the other way around. So, because the Liouville central charge is negative, it's a Timelike mode. We have positive matter central charge. So the Xi's are positive. They are real. They have positive central charge. Central charge bigger than 1, bigger than 25 in general. So more than 1 to 25.
Okay.
I mean, I think you were saying it the other way around. Yeah. Yeah, so we're in the Timelike Liouville range. Central charge of Liouville is smaller than 1. So matter central charge is bigger than 25. So in general, you can have it's super critical string theory. Okay. Yep.
Vision here, like I have like 526 dimensions, and with my string theory, like you have this Timelike Liouville thing.
Yeah.
All right, cool.
One time and as many as you want of space. Yeah. Well, as many, minimally 25 actually. Okay. So great. So I don't know why I'm on this slide again. Okay. So therefore we needed to, the question was, what is the analytic continuation of the 4-point function to real energies? Is it well defined on physical states of the gravitational spectrum? And for this, we had to figure out this analytic continuation. And here we use some techniques of string field theory. Well, it was Harold was the inspirational source for that. But the point is that basically what you do is you start with imaginary energies, because that's what the bootstrap did. That's what they knew and they used. We want to continue these external energies, 1, 2, 3, and 4 to real. But as I said before, well, all of them to real in principle. But as I said before, the integral diverges at real energies. So the usual wig rotation that we do in QFTs does not apply here, basically because the arcs at infinity diverge. And in fact, they diverge. I had added this here, but it didn't show. They diverge as some quantity that is smaller than 1 to the minus 2e sub s squared. And Harold tells me that that is also the divergence of vertices in string field theory for loop amplitudes. So it's a similar type of divergence here. But this is at the level of the correlator, unintegrated correlator. So then what are we to do? And so for this, we use this prescription that was also used in string field theory, which is the following. You define the correlators with everything imaginary energies. Then the 4-point function is finite and crossing symmetric. And then you analytically continue the external energies only. While, first of all, keeping the contour ends fixed at imaginary energies. So you don't rotate the whole contour like here. You just keep this end fixed, so it does, the integrand doesn't diverge. But then it's key that you don't, that as you do this continuation, the poles will move. And what you have to do is deform the contour so that the poles don't cross it. So this is what you have to keep track of. How do the poles move when you analytically continue to real energies? So this generalizes the weak rotation. And so we did this for Timelike Liouville. We checked the behavior of the poles. And that's where this question is relevant of the form of the 3-point function. In this case, is actually very special, if you want, because the poles of the integrand do not move at all, in fact, when you analytically continue the external energies to real. Because here, each pole, it doesn't depend on the other energies. Therefore, when you analytically continue, there are no poles moving, and therefore you do not need to deform the contour at all. So the upshot, if you want, is that you can basically keep this integration contour like this over imaginary energies and analytically continue simply your external energies to real, and the 4-point function with that contour is still finite and crossing symmetric. And you can identify this as your internal spectrum, but your external spectrum of energies can be more general. Okay, so this is it for this part. This is just the summary. Maybe I pause for a second if you have any questions. Drink some water. Mm-hmm. Right, so the poles are on imaginary energies. You just shifted I epsilon away. It doesn't make a difference, in fact, because the energies are quadratic. The dimensions are quadratic in the energy. Therefore, whether you give it plus I epsilon or minus I epsilon doesn't make any difference. Yeah, it's a bit of a special case, but yeah. So it's kind of an I epsilon prescription, whether you do plus or minus I epsilon is not like retarded advance or things like this in this case. Yeah.
Just one comment is that a similar thing also happens in the space like Liouville. The usual DOZZ formula only applies in a certain range of complex alphas. But if you want to go outside of that starting range, you also need to keep track of these poles and deform the, the contour of the internal primaries in the space like Liouville. So there's a paper by Alexei Zamolodchikov from around 2005. And it's relevant because the special values of alpha that show up in the non-critical strings actually are not in the original sort of defining domain of the DOZZ. So you have to keep track of the similar kind of poles there.
I see. So in that case, they have to deform the contour.
Yeah.
In that case, the poles do move.
The poles move depending on the external parameters.
Yeah.
The external alphas.
Much more complex than in this case, in fact. So
yeah.
In fact, this Timelike Liouville is nicer. Yep. Thank you. Thanks.
So if you include these real energies in the OPE expansion, then it seems they will also propagate in the internal necessarily, because suppose you take the 4-point function of 4 imaginary energy states, they will have an OPE, non-vanishing OPE with a real energy state in the internal channel, no?
No.
So once you include it in the spectrum, it seems it also propagates inside.
No, I don't think so. In the OP, they will only go to imaginary energy.
But if you have imaginary, real goes to imaginary, you also have an OPE, which is imaginary real goes into real. Is then also no vanishing. No? And there is no. So suppose you take 2 real external states and 2 imaginary, then you would have a real state in the internal channel. No?
I don't think so, but
yeah, I mean, the OP is rotation invariant, no? If AB goes into C, then AC also goes into B. Yeah. So then how does it, so are you saying then that this is you should really include it in the spectrum, the real energies, and it's a well-defined 4-point function, or it's not a? Right. And so in the spectrum they are there. The both operators are in the spectrum. Okay. Yeah, that's true. But just when I define a CFT, isn't it? I need the conformal weights and the OPs, and that should define it completely. I see. So it depends a little bit what you do.
Okay, I'm not sure I understood the answer to the question, but maybe we can. Yeah. Yeah. Okay. I see. Yeah, but that's an imaginary energy. Okay. Perfect. Thank you. Okay. All right. So let me move on now. And I go on to talk about the sphere partition function. So the first thing I need to do is show you that there is a sphere saddle. So this is again the action for Timelike Liouville. And now we pick the fiducial, now not to be flat, but to be the sphere. So this is the fiducial metric H. We fix it to this sphere. This epsilon here is just the radius squared of this. It can be anything. It's just the radius squared of this fiducial. So this Ricci scalar is just a constant now, different from 0. And the equations of motion of this action you can derive. They're very easy. They have this piece. This is from the background, which is now a constant and just is exponential. And this has a real solution. So of course, this just becomes 0. And then as long as mu is positive and q is real and positive, this has a solution within this regime, which is just basically given by this. This form doesn't matter, but the point is that now the physical metric G, which is e to the 2 omega h, is now also a sphere, but now the radius from the fiducial to this has changed, and the radius now depends on the cosmological constant mu and the Liouville couplings. Okay, so this is the solution of the Liouville field, and therefore we can do saddle point approximation around this saddle. So what we do is we go back to the path integral over the Liouville field guy. This is the Timelike Liouville action. We'll expand around this saddle point, and we computed the first correction in this 1 over q squared or beta squared perturbation. And the first thing to take into account is that from the volume of the diffeomorphisms after the gauge fixing, there is this residual volume, which is the volume of conformal transformations. So this is there. It's this residual conformal symmetry that we talked about. And the problem is that this volume is infinite. So the way to deal with this, or one way to deal with this, is to say, okay, then maybe I can further gauge fix to reduce this volume. And in fact, you can reduce it further down to the volume of SO3, which is the symmetry of the sphere. And this volume is actually finite, and therefore you can just do it. You're left with this volume here, and then the answer might be finite. Okay, so how did we do this gauge fixing? So what we did basically is, okay, we're in the sphere, so we can expand the fields in the spherical harmonics, the real spherical harmonics, and we have these chi-LMs. And now, because from these 6 generators of the SL2C, we will fix 3 of them. Basically, we can fix the chi-1Ms to 0. So the chi-1, 1, 0, and 1 minus 1. So actually, it's a gauge fixing that had already been used. Huh? So of course, you do this gauge fixing, and then you need to take into account the Faddeev-Popov of this gauge fixing. And this you can compute. You can compute exactly, and this is what you obtain. So there is a prefactor here that has a q cubed contribution. This is the main contribution. So therefore, there is an overall, like this gauge fixing determines the overall q power of the partition function. And then it also has 2 corrections in 1 over q squared, 1 over q cubed. And well, we were just interested in the first correction, so this will come into the first correction, and therefore it also changes the gauge fixing, also determines the corrections in beta squared. Okay, so now we can go back to the integral, and this is just the path integral of the Liouville field. Here we have the contribution of the saddle of the sphere. That is the volume of SO3. Now we introduce this Faddeev-Popov determinant, which, because it depends on the 2m modes, it will contribute to the Gaussian part of the integral. This is the gauge fixing Dirac delta. And then here we basically expand the action up to order beta squared. And so this is what we have to, we just expand, we just compute this perturbation theory. And so wanted to make some comments. First of all is that once you put in the saddle and you expand around the saddle, in here there is no longer any dependence on the cosmological constant. So the cosmological constant only appears here in the action on the saddle. And that dependence, therefore, is exact and is completely determined from the get-go. And in fact, it's given by this mu, which was the cosmological constant, to the minus q over beta. So this is the exact dependence. And in fact, this dependence, you can derive it from critical exponent arguments already from the beginning. Second comment is that also the action, even though there is the upsilon here, upsilon is the radius of the fiducial metric. Therefore, the final answer should not depend on upsilon because that was just our pick. This action does not depend on upsilon because there is a square root of h sitting in front, which cancels these upsilons in the denominator. So this, it doesn't appear anymore, but the measure depends on upsilon, of course. And this dependence is such that it is given by the Liouville central charge. So it has the usual anomaly dependence of a theory on the sphere. And this is such that, of course, you get the same from the matter and from the ghosts, and therefore anomaly cancellation of the central charge ensures that there is no upsilon dependence in the end. So this works out nicely. You can complete this explicitly. Then the next point is, okay, this is an important point, is the negative kinetic term. This is an unbounded Gaussian. How do we deal with this? So for this, we followed the prescription of Gibbons, Hawking, and Perry, and we basically rotated the contour of integration. So you do chi goes to plus or minus I chi. Sign, it's up to you. So of course, this then gives a well-defined Gaussian. So this was a check. I would say, okay, let's use this and see if we get something sensible. I mean, a priori, we didn't know whether this would work or not. And so then you can do, once you have rotated this is just a normal Gaussian, you can integrate. So you expand this chi in the modes, in the spherical harmonic modes, the chi LMs. And so here you get this LL plus 1 from the kinetic term. And then you get this piece here. This is just the quadratic part of the integral, so the chi squared. So this is like the partition function of a massive scale, free massive scalar on the sphere. Just that now it has like a negative mass. So that you need to take into account. But otherwise you can do it. Now the L equal to 0 mode, now this is 0, and therefore this now becomes an unbounded Gaussian, so you have to weak rotate it back. And this weak rotation back gives an overall phase to the partition function. And then, well, the L equal to 2 modes are not just any Gaussian because they have the contribution from the Padev-Popov. And then all the other modes you can simply do. You have to use a regularization method like the heat kernel and so on, but you can compute that. And then finally, you have to take into account the interaction terms. So this come from this cubic vertex and this quartic vertex. And so you can draw these diagrams here. And what's remarkable is that this double tadpole and the cactus actually both are UV divergent, but they're such that they cancel exactly. So all the UV divergences cancel exactly. And you're only left with this melon diagram, which is finite. I've just written the contribution here, but it's not important. Just want to say that it is finite. That's the remarkable thing. So we do not need to introduce counter terms in this perturbation theory. My job. Okay, so then we plug this in, and this is the result that we got. So I should also say this is the work that I did with Dionysius and with Beatrix. So let me just go over it. So this plus minus I again is the phase that comes from the L equal to 0 modes. Then there is some constants. Then there is this cosmological constant dependence. So this exact, as I said, comes from the saddle. And then there's this UV cutoff here that comes from the integration measure. This is just the usual UV cutoff dependence of a theory and the sphere, but it is such, it comes out such that, of course, it has the same exponent, so this is dimensionless. Then there is a overall beta dependence, so dependence on the gravitational coupling. And in particular, this power here is also determined by the gauge fixing, so by the Fadeev-Popov determinants, which have an overall beta power. This is the leading piece, and then this is the first correction. This 27/8 I've singled out because, again, this is the correction of the gauge fixing. And then there are some other pieces, and in particular, there's a contribution of this guy. And there is also some ambiguity here, depending on this UV cutoff, of course, and so on. So here are some of the comments I wanted to make. So Timelike Liouville gravity with unitary matter enjoys a finite semi-classical expansion. So it suggests that it's finite at all orders, not all just at this order. In fact, Beatrix did the calculation to the next order, and she also found exact cancellation of the UV divergences. The weak rotation of this contour a la Gibbons-Hagen-Perry seems a sensible prescription. In fact, in the next slide, there is a further test of this. The radius anomaly cancels, as is expected, so everything is consistent with conformal symmetry. And importantly, the diffuse gauge fixing contributes to the leading beta dependence, as I said. Okay. Okay, and now one thing that we could do with this result is compare to what is known for space-like Liouville. So in space-like Liouville, from the bootstrap result, you have an expression for the partition function on the sphere. So what you can do is take this result, analytically continue it to the Timelike regime, and then expand this perturbatively and compare it to what we computed. Yeah, so this is what we did. This is the partition function for Liouville, non-perturbative because it's what bootstrap gives you, so it's a full result. Analytically continue it to Timelike, and then take the semi-classical limit. And we compare it to what we had obtained with an explicit calculation of the Timelike path integral. And what we found is an agreement, but up to this factor. So there is, first of all, there is this factor of I here. This was the phase that we were getting from the zero modes. We believe this is not very significant simply because in the bootstrap, the way you obtain this partition function, there is an ambiguity in the normalization. So, you know, you could put this I by hand if you wanted in your normalization. So this might not be that significant. What's more significant is this factor here. So this one is clearly coming from the sphere cell that we computed, but then there is also this factor here that's telling us that the bootstrap result of the partition function is suggesting that one should be taking into account the second saddle. And the second saddle actually, if you take the sphere saddle that we had expanded around, and you just shift it by this piece here, I pi beta, then this is also a solution and exactly reproduces this contribution here, because this only changes the saddle contribution in the action. It doesn't change anything else. So you get exactly the same with this prefactor here. So yeah, the matching was good. It was also a good test, if you want, of the rotation of the contour of integration, just that maybe we had to take into account this other saddle. Yeah.
Yeah. So what metric does this correspond to, this other saddle?
What?
What metric does this correspond to?
It's the same metric, actually.
Ah, okay.
Because you see the metric, the physical metric is e to the 2 beta chi. So e to the 2 beta times this is e to the 2I pi. So it's actually the physical metric doesn't say this. It's a complex saddle for the Liouville field, but the physical metric doesn't see the difference. Yeah. Yeah.
Infinitely many of these with IN pi over beta, and why do you have only just one?
That's a very good question. I don't know.
Because in the space-like case, that's what happens. You have to sum over a whole infinite series of them to get the right.
Yeah, so I don't know the answer, and it's definitely a good question. So indeed, you can actually multiply this by n integer, and all of them are solutions. All of them leave the physical metric invariant because it's e to the 2I pi n. So why wouldn't then all the saddles contribute and only the n equal to 1? I don't know. It might have to do with the analytic continuation of the gamma function. So one second. So we talked about this, as I said before, the difference between the space-like and the time-like is that there is this inversion of these upsilon functions in the correlators. Eventually, this partition function of space-like, the way it's computed is by integrating the 3-point correlator. It's some trick in Liouville theory. So because of this relation between the space-like and the time-like, they are related by this sort of inversion. There is something happening with the saddles. And it might be that for some reason, the analytic properties of gamma functions and so on, in this case, you're only recovering this one. It might be that Dionysius and Beatrix have a better insight by now on this point, because I think they looked into it at some point. If you happen to, or I can also ask them and see. But I certainly don't have a good understanding, and definitely not from the point of view of gravity, why only this cell should be taken into account. Yeah.
If it's the same physical metric, how can the actions be different?
Well, we're integrating the Liouville field, right? And the Liouville field does change. I mean, we're in the conformal gauge. In the conformal gauge, we isolate the Liouville field, and the Liouville field is different because it's shifted by this piece here.
Okay.
So for the integral of Liouville, these are different saddles. So this was a logarithm, and then this is a logarithm plus this term here. Yeah. Yeah. No. No, I don't think so. Well, I mean, sorry, up to this factor here, yeah. This piece, it's you just evaluated in the saddle point, so let's see. So the kinetic term gives 0. It's the linear term. So you see you have Q, the Ricci scalar times the Liouville field. So the Ricci scalar is just a constant, and then you get this Q over beta. So you get this 1 over beta squared. I think that's where it comes from. Yeah. Then one thing that this is suggesting also is that because we have a non-perturbative expression for this guy, for this partition function, this suggests that we can propose also a non-perturbative expression for this sphere partition function, which is basically given by this before taking the beta going to 0 limit. And in that case, this is what one obtains. This sign here, ambiguity, again, is related to the ambiguity of the rotation of the contour, integration contour. Otherwise, it's given by this here. So this is, again, this partition function one obtains with a bootstrap rotated to the time-like regime. I wanted to make the comment here that in particular, if we go to the critical strings, so basically critical strings, we put Q to 0. So there is no background charge. There's just a time-like free scalar and then 25 free space-like scalars. Then Q is 0, and therefore beta is equal to 1. So this is what reproduces critical strings. And then in particular, we put mu, the cosmological constant, to 0, so no cosmological constant. And in that case, you get that this partition function is equal to 0, basically because of these guys here. So these gammas sorry, I should have said that. These little gammas are, so let's say little gamma of x is gamma, Euler gamma of x divided by Euler gamma of 1 minus x. So when beta is equal to 0, x is equal to 0. So the gamma of x minus 1 is infinite. So it basically gives this is 0. And in particular, then if you put mu to 0 afterwards, you nevertheless get 0 unambiguously if you want. Yeah.
Shouldn't be this non-perturbative proposal symmetric on the bit that goes to 1 over bit?
It should. And I think it is. So
the prefactor doesn't look like.
Yeah, it doesn't look like it. Yeah. Yeah, but I guess he's wondering about this.
There is the power q of a beta.
So this piece is not problematic because indeed when under the duality, mu also has to change. And this piece here, I wondered about this too. I think in the end it was that it doesn't look invariant, but it is. Let me come back to you about this later. It should be. It should be.
And another question. So if I understand, this is the limit of the usual critical strings in 26 dimensions.
Mm-hmm.
Yeah. Mm-hmm. And is what about the limit of also critical case, which corresponds to 2-dimensional strings?
Mm-hmm. So in that case, you mean C Liouville equal to, well, I mean, it depends on, so which matter central charge?
Or this corresponds to space-like Liouville, yeah.
Normally what I think is considered 2-dimensional strings is you couple space-like Liouville to C equal to 1 matter. In that case, Liouville is space-like, it's central charge equal to 25. Then that would be the regime of space-like Liouville. So you would have to put Q imaginary here if you wanted.
But the
partition function is not?
The sphere partition function in that case wouldn't be vanishing.
Wouldn't be?
Vanishing.
Vanishing. So no, I don't think so. No, because in that case, Q squared, Q would be 2, B would be 1, and this would be gamma of B squared. So gamma 1 minus B squared, it might be 0 also. But you're saying it shouldn't be.
Well, I don't know. But,
okay, just like if I think of it this way, in that case, C Liouville would be 25. So Q squared would be 4. Beta would, like B, this B would be 1. And then this gamma would be gamma of B squared. So we would have a gamma of 1 here divided by gamma of 0. So okay, I don't know.
Well, we can consider this later.
Okay. So that was the end. So just to summarize, Timelike Liouville gravity with a positive cosmological constant and coupled to matter has a finite sphere partition function. And this I already said before. And just very shortly, but a bit of an outlook. Of course, these are questions, well, they need to be set because this is a theory of with a time-dependent background. I think it would be very interesting to use it to see what one can learn about Lorentzian signature. in space-time. In terms of the microscopic, so for instance, what we were interested in computing the sphere partition function is because it reproduces the entropy of the sitter, of the horizon of the sitter, simply because the sphere is Euclidean, the sitter. So for instance, because we got this expression for the partition function, we had this, there is this analytic expression for it. One can try to give meaning to all these dependencies. In particular, for instance, there is this logarithm of the cosmological constant with all these quantum corrections here. Now, I don't know from the space-time perspective, if this is to reproduce some on-shell action, it should reproduce some finite entropy, like the classical entropy of some solutions, whether this analytic dependence can give any interpretation. And then something that I'm currently doing, and I think is also interesting, is to study the brain solutions of Timelike Liouville, which have also not been explored at all. And, you know, for a space like there are these ZZ and FZZT brains, which have had tons of development. So I think it will be interesting to explore similar things in Timelike Liouville and see, you know, boundary conditions and time and so on. Yeah, I had some extra slides, but maybe I can talk to whoever is interested afterwards. Thank you.
Questions? Time for few questions, but you can
Well,
keep
actually,
many
what time
questions
is it?
for the
That was
discussion.
1 hour and a half.
Yeah,
Wow.
but we started a bit late,
Mhm.
so we'll have time for a few questions. Okay, well, there were many questions during the talk. So unfortunately, there was also a comment by Harold Erbin in the chat, but I see that you are not connected by Zoom because you are following it. So let me read his comment. Sorry. Oh yeah, you can put it to the screen. Okay, let's see this. Okay, I think that's the answer to Ivo's question.
Oh, this
question was that.
Maybe that was the answer to Ivo's question. Yeah. I don't know if Harold is online, if you want to comment live, but I'm not sure how that addresses the question of whether if you had an OP, you would have a, but.
Yeah, I'm here if people can't hear.
Yeah.
Okay. Yeah, so it's a remark we had often, like if like it's not really a CFT what, I mean, proper CFT what we do, because in a CFT you just start to look at state and then include everything you can get by OP. But if you follow this logic, for example, in the original theory you defined like from Ribot and Santiacara, the OP with any state with complex alpha makes sense. So you could say, okay, in principle, we should just include everything, but then you get problem in defining the 4-point function. So the way you can define the theory in this case is that you just look at all the states you have and have some non-trivial period between each other. And at the end, you just keep the one for which you can define a 4-point function and 5 and so on. And the question of which states you want to keep depends on which physical problem you want to look at. So in Ribot and Santiacara, they just like want to do something simple and say that external and internal states should be the same. But like it's not an important requirement to define your theory. And like in Ashok's prescription in string theory, it's a bit what you do when you say that you have a contour. So the external states can have real energy, but the contour can do whatever you want. And if you look at states which are on the contours, they can have general complex momentum. But it's still like one theory which is defined by a very specific prescription which gives unique answers. So it's like, yeah, it's not a CFT in the usual sense, but it still satisfies all the requirement to be a CFT, like conformal invariance, bootstrap, and so on.
So the answer would be that if you had such an OP, it would go to a real energy, but you shouldn't include that when you decompose the 4-point function.
Yes. Because, so yeah, you write the 4-point function in terms of this OP, but you decide about where you sum. So you just decide what you include. So OP makes sense in it for any complex alpha, but you should not include everything.
Thank you.
Who has a last question?
Hi, Harold. When you choose states in a CFT, you may have problems with modular invariance, or
Yes. So in fact, yeah, this was checked by also Ribot and Santachiara for Timelike, but with their states. So they could show that if you get the 4-point, so crossing symmetry of the 4-point functions, and it also implies the modular covariance of 1-point function, which is sufficient for modular invariance at any order. So they use the proof for space-like, which just hold also for the Timelike case. And in our case, because we don't have to move the contour or anything, like the proof should still hold. The point that in our paper, we just focused on sphere partition functions. So I don't want to say that modular invariance holds for sure, but I would expect the derivation to continue to hold.
Okay, thanks.
So unless there is an urgent question, which all other questions are recommended to keep for the discussion session. And I think we can thank Teresa again and go for the coffee break.
Thank you.